Hey everyone, Mr. Cummings here, and welcome to this video on calculating motion in different reference frames. So the first thing to discuss here is that as we go through the equations in this video, we'll be dealing with inertial reference frames. So the equations that we're using only work if the motion that we're dealing with are in reference frames that are inertial. So what does that mean for something to have an inertial reference frame? It means that the reference frame is not accelerating, therefore it is moving at a constant velocity or it's constantly at rest. So we'll jump right to it and we'll take a look at an example here where we have two carts, and I've drawn these carts so that there is a little eyeball on top of it. So we're going to imagine that these carts can see one another. So if we have a cart VA, or a cart A moving at VA 3 meters per second in the rightward direction, we're going to say VA is the velocity of cart A with respect to the ground frame of reference. So we're measuring this 3 with respect to some stationary object here on the ground. So VB would also be the velocity of object B relative to the ground. So you can kind of imagine if we have an observer here standing on the ground watching these two carts, this is what they would measure for those velocities. And then if we wanted to know what the velocity of object A is with respect to B, in other words, how fast does object A appear to be going compared to object B or from object B's frame of reference, we would write that as VA with respect to B, or VA slash B. That's the velocity of object A from object B's reference frame. And if we did that, it would look like object A is moving towards object B at 2 meters per second. If we flipped those reference frames, velocity of object B with respect to A, so how fast does object A see B moving, then we would say that object A would basically be seeing object B getting close to it because object A is going to be approaching object B. So we would say that object B has a velocity of -2 relative to object A's reference frame. So what does this actually mean? It means that object B sees object A traveling towards it with a velocity of 2, where object A sees object B traveling towards it with a velocity of -2. The reason that we're getting a negative sign here is because we are defining the right as the positive, since both of these have positive velocities. If object A is moving in the positive direction, but it sees B getting closer to it, then we would say that it would look like object B is moving towards object A, which would be a leftward direction there. So if we wanted to draw a vector arrow to kind of show these velocities, we would do so like this. So how did we actually get these numbers for A's velocity relative to B and B's velocity relative to A? So we used the relative velocity equation, which is right here. So we said if we want to calculate the velocity of object A relative to object B, we should just take the velocity of object A and we should subtract the velocity of object B. And the answer to doing that vector subtraction will give us a relative velocity. But we want to generalize this to make it a little bit more universal. So if we go here, we can see this is the same equation, but when we took object A and object B's velocity, those were both relative to the ground. So we could technically write them as VA relative to the ground and VB relative to the ground. So I haven't really changed anything here. We're just defining what we took those objects' velocities relative to. So now we'll further generalize this equation. The ground is just a stationary reference frame. So if we want to replace the ground with some arbitrary letter, we could call it observer C. So if we do that, we can see that the velocity of object A relative to the velocity of object B is equal to the velocity of object A relative to some other reference frame, in this case the ground, but we're calling that C, minus the velocity of b relative to that same reference frame. So generalizing this, it doesn't matter if we have the velocities relative to the ground or relative to some other observer. We can use this equation to figure out the relative velocities between two objects. Now, this is great because it allows us to rearrange the equation, and it becomes a powerful tool for us to figure out relative velocities to each other, and also something called frame switching, where we want to change the frame of reference of some object velocity. So over here on the right, we have our general equation, VA slash B. That's equal to VA slash C minus VB slash C. So notice here that the answer, VA slash B, is the first, so A, relative to the second, which is B. And notice that both of these objects are relative to the same letter C, the same observer C. So those would cancel out when we do the subtraction. Now let's say we had the relative velocity of one object and one object to the ground. If we rearrange this equation and we wanted to maybe find VA relative to the ground, we could say that that is VA relative to B plus VB relative to C. So once again, our answer, VA slash C, is the first relative to the last term here. And for this equation to work, our inner frames here, these B's, have to be the same. So if I had something like VA slash D plus VB slash C, that would not work because the B and the D are mismatching on the inner. Those have to be the same. So now let's take a look at an example problem where we have a boat moving 5 meters per second relative to a river, the river flowing 3 meters per second east relative to the ground, and we want to know the boat's relative velocity to the ground. So we'll go ahead and define all of these variables here. Now we're going to solve this by using the frame switching. So we're going to take the velocity of the boat relative to the river. We're going to add the velocity of the river relative to the ground. We'll see that the rivers are the inner terms and they cancel out. And if we plug in our numbers, we should get the velocity of the boat relative to the ground. So something to note here is that this simple addition of adding 5 and 3 works because both of the vectors are parallel to the horizontal axis. They are both east. If one of these vectors were west, then we would just change the sign and do the same arithmetic in the same way. So to visualize this, we can show the velocity of the river relative to the ground and the velocity of the boat relative to the river, and we would just be doing a simple vector addition. But it changes if we have vectors that are perpendicular to each other. So taking a look at a problem where we do have perpendicular vectors, we have a plane flying relative to the air, and we have wind blowing relative to the ground. We want to figure out what the plane's velocity is relative to the ground. So we have VPA, which is 200, and that is in the north direction. And we have VA slash G, which is the velocity of the air relative to the ground, and that is 50 kilometers per hour in the eastwards direction. Because these vectors are perpendicular, we do need to look at them graphically. So we have our VPA moving to the right or the eastward direction, and we have VAG moving upwards or to the north direction. So if we draw these as vectors, we will see that we can't just add their magnitudes. Instead, we have to do the Pythagorean theorem to figure out what that resultant velocity is. So this equation that we have for relative velocities still works, but we do need to remember that velocities are vectors even if they're relative velocities. So we have to obey vector rules, and in this case we would want to show that the vector addition would be the Pythagorean theorem of 250. And that's going to be it on this video, calculating motion in different reference frames. Thanks for tuning in, and I'll see you next time.